Hello friends, welcome to this session of Learning R, and in this session we are going to learn again about neural networks. In my previous video we fitted neural network model to resin data where we classified resins based on numeric predictors. One of my viewers asked me to make a video on neural network using character predictors. And in this video we are going to fit neural network to housing sales data. We will predict sales price of houses using character predictor variables. Let's import the data first, and to import the data we have to set working directory, and this is the folder in which neural network is the folder in which this housing valuation data is there, and this data set we are going to use in this session. I am clicking in this address and copying it and bring that to my script, where I will use setwd function in inverted quote that path. I will change this single slash to double slash and run that, and here you can see that my working directory has been set. Now using list.files I will get name of all those files, will run that, and here that data is there, housing evaluation.csv data we need. I will copy that and will use that in a function data read.csv, and I will paste that housing.csv, and the data will be saved in the object data. I will run that, and my data is there with me. Structure I will determine data and run that, and here you can see that 32 variables are there and 1454 observations. Many variables are integer and many variables are character variables. Now we need to convert these character variables to factor variables, because neural network treats those as numeric variables only at the back end, and the functions which we are going to use will convert those factor variables to dummy variables. Don't bother much about those specifications. Dummy variables you will understand as you go on learning this statistical model fitting, and we'll see the summary also to know about range of the variables. Summary data. Now you can see here that this variable has that ID. ID will not require for predictions, because ID is unique to each observation. Lot area starts from 1300 to 2,15,245. A very large range is there. Lot shape range 1 to 4, a very small range. Then these are character variables. Again, overall quality 1 to 10. These variables range is quite different, and some variables are very large, some variables are very small. Therefore, we need to scale those variables before starting working on this data. Before starting work on the data, we'll convert those character variable to factor variables, and for that we have to select character variables, and I'm going to use deployer function for that selection and mutations, library deployer, and I will collect categorical variables in this object categorical variables data, and then I will use the select function for that, and where function to get those categorical variables is dot categorical, and when we run that all those categorical variables will get selected. That categorical is not right one, character I have to write character. Run that. Now categorical variables are there, and I need names of those categorical variables. This subset of data frame is there, but I don't want the data frame, I want names of those columns. Therefore this names function, and I will see whether I have got the columns or not, and these are the 11 categorical columns which I got here, names which I got here. Now I will use these names to convert those to factor variables, and now I will convert these categorical variables to factor variable in the data, and this in data object only I will do the changes. Mutate is the function to do that, and to get all these mutated I will use the function across. Inside across I will use the function all of, and then the cat vars, name of the variables which I want to convert. And then after this cat vars, the next argument for this across function is as dot factor. And when we run that, you'll see that the little mistake is there in this spelling mistake. We'll run that. Function worked, and we'll see the structure of data again. And you can see here that those categorical variables have got converted to factor variables, and all are factor variables with different levels. Now we'll remove the ID variable which is unique to all those observations, and this is not at all useful for our model fitting. And for that purpose, I will again go to the data and data object again, select minus ID and run that. It says that ID variable is not there. Yes, little spelling mistake is there. ID, and run that. Now we don't have ID variable in our data, and at this moment we'll check whether the data contain any missing values or not, and if missing values are there, we'll replace those with the most probable one using imputations. And for that, I will call library vim to see those missing values and run that. Library vim has got loaded. AGGR function gives us a plot where missing values will be shown in red. Now 3 variables contain missing value and 1 variable contain missing value more than 0.05%. These less than 0.05% missing values, we can omit those observations, but as this is very large, we will not omit the observations, we will go for imputations. I need to know the names of the variables which contain missing data, and in this those variables names are not visible. Even if I zoom that, still those names will not be visible. Here after fireplaces that variable is there, but don't know which variable that is. After fireplaces, that garage type variable is there which may contain the large amount of missing data. To know those, I will use a function called as callsums, and this is from the base R only. Is dot na function, and data will be the argument. Now is dot na will provide me a data frame where those na values will be mentioned as true, and if no na value is there, that will be mentioned as false, and all those trues will be summed from each column, and the columns which are showing the numbers contain the missing values. That year built is 1, then living area is the second one, and garage type is the third variable which contain the missing data. And we will use mice package to impute that data. We can do that using caret package functions also, but here we are going to use those mice package, and that imp will be the object where I will use that imputation model and mice data, and this is sufficient now to get the imputations done. And those imputations you will see that are taking place in the 3 variables, year built, living area, garage type, and that imputation is going on. It will take a little time based on speed of your processor. Imputations have taken place. Now that data no miss I will use as to save the imputations, and complete is the function from mice package to get the complete data from the imputed model. I will run that, and now that data no miss is there, we'll confirm again whether those missing values have got replaced or not, and data no miss will use, and I will run that. Now you can see no red colors are there, no red bars are there. This means that all the missing values are replaced with the most probable one, and believe me that mice package does very nice work. You can use Amelia or random forest also, miss forest also, to get the imputations done, or caret package pre-processing, KNN impute or other impute models you can use. Now we will scale and center the data to make its magnitude equal as we discussed above, and for that scale and center I will use the pre-process function, but before that I will get that pre-pro model and pre-process function from caret package. I have to call library caret for that, library caret, and run that. Then preprocess function, I will type first few alphabets so that I will get that function, and here I will use the first data no mix no miss object, and the methods I use will be scale. The two methods I am going to use, therefore I am using the vector here. The scale shall be in inverted quotes because it's name of the method, and next name is center, and scaling and centering will be done, and I will run that. We'll get a model here, and from that model I will get the data pre-pro, and there predict function from caret package I am going to use there. That predict function require model as the first argument, and then the data in which we want the imputation. That data no miss, we want to not imputation, we want to get scaling and centering. And now that scaling and centering has done, we'll see the structure to appreciate the scaling and centering. Data pre-pro, run that. Structure is not the proper function, summary is the proper function. Summary data no miss, and here you can see that the data has got centered at no, centering has not done. I not me miss, pre-pro is the data where centering has been done, and here you can see that centering has been done, mean at 0, and the scale is almost equal for all those variables. Now next important step is splitting the data into training and testing data, and for that we are going to use the create partition function to get indices to be included in the sample or training data. Index object will collect those indices of the rows which we will use in the training data. Create data partition, and the sampling of these rows shall include all the variations which is there in the data according to the outcome variable, and for that we'll define the outcome variable, that is data pre-pro, that dollar sales price is our output variable, and P is equal to 0.8 because we want 80% rows in our training data, and we want the output not as list but as matrix, so that we can use that directly as index. I will run that. Now index is there, and using that I will have the train data is data pre-pro because I want to sample from the pre-processed data, and indices of those in the training data, and I got the train data. We can see that n row train data is 80% of the train data, 80% of the n row data pre-pro, and it's almost 80%, little more just because of that rounding thing. Then test data we are going to collect, test data, and in test data the same one, data pre-pro, and indexing, just will use the minus symbol before the index to omit out the rows which are there in the training data, and this test data will serve as unseen data for model validation, and run that. Now that n row of test data, we'll see n row of, the spelling mistake is there, n row of test data, and that is 290, almost 20% of the observations which are there in our data. And now we'll define train control, that means method for resampling and validations, and tune grid for hyperparameter tuning. And for that purpose I will put that here, train control and hyperparameter tuning, which we are going to do here, and for that purpose here that comment shall be there, and the train C will be the object where I will put that train control, and this is the train control function, and method I am going to use repeated CV. In repeated CV, that will break the sample, not resample, repeated CV, break the sample into groups which will define here using number is equal to 10 subsamples will be there, and it will fit model on the 9 samples using those as training data, and remaining sample will be used as the test data for validation, and that very extensive cross validation will be done. To get tune grid, we'll use the expand grid function from base R, and this expand grid function is very useful to get a table where the combinations of all those will be obtained. In the size means how many number of nodes we want in the hidden layer, those 3, 5 and 10, this many. Then decay is the weight decay to avoid overfitting, that decay values will be 0 0.01, 0 0.1, 0 0.5, not 0 0.1, 0 0.5. Okay, these 3 values we are going to use in decay and run that. Now these two train control and hypertuning parameter process where we did. Now it's time for us to feed the model or train the model, and for that we'll set the seed. Set dot seed is equal to, we can have any number here to get reproducibility in the random processes, and there I will use the object mod to save the model function, and there I will feed that train, and first it will require the formula, and that formula will be a sales price determined by sale price. I'm copying to avoid the spelling mistakes, the tilde symbol, and shortcut for all the variables which are there, that spaces, and method is equal to, in bracket, nnet, and tune control, train control, we'll see the arguments for this train function, because I forgot about that. Train function, caret package, and there a pre-process we don't want here in train. TR control is the we require. TR control is equal to train C object which we defined earlier. Then tune grid is equal to tune grid is equal to tune grid, tune underscore grid, and lean out, that is linear output, and we require that to be true for the regression models, and that's it. We'll close this bracket to complete the train function, and we'll run that, and it says that data argument is not there. We forgot to have the data. Data here is equal to data pre-pro. This shall not be uppercase, and run that. Train C, again spelling mistake is there, therefore I always go for copy pasting. Train C I forgot to run, I think. Tune grid, and now let's see whether it runs or not. Yeah, it's running and neural network model is getting fitted, and all those options from the tune grid will be used there. First it will go for size 3, and then all these 3 decay values one by one it will use to fit model. Then 5 it will fit for 0.1 and all that, and at each time for each fitting it goes for this repeated CV also, and therefore many different models, 3 multiplied by 3 9, and this time for each one 9 models means 9 raised to 9, almost 81 model it is going to fit, and out of those 81 it will provide us the best fitted model. We'll wait for the model to get fitted. A model got fitted, and now we'll see summary of the model, summary of the model, and run that, and now these all are values of net. If you fit the model using neural net function, then you can have the plot method to see the neural network as we saw in the previous video, but here we'll not go for that. Plot model, we'll see here the best tuned model. These decay values on all those are there. 0.01 decay value and 0.5 decay value is this green one, and this green is providing us the RMSE, repeated cross validation, which is the measure for validate the regression models. RMSE is the root mean square error, and root mean square error smallest is the best one. That means model got fitted quite properly, and this with weight decay 0.5 and hidden units 10, the model is the best one, and that will just see using mod, and this mod object information is here. I will just improve that. Neural network 1454 samples, 30 predictors it used, 32 were there. We have removed the output and ID variable, and that those decay and all those values are there for each size, and you can see here for this one we have the list RMSE. Here also that list RMSE is there, but not much significant difference is there, and here that MA and all those matrices are quite good for that. Therefore this final model, or we'll see the mod dollar final model also, final model, and when we run that, this final model is there, and options were linear output units, decay was used at 0.5, and how many variables it used, and to find out almost 10 variables it have used, and this is how we fit the model. And to validate the predictions, we'll have the predicted values, predval, and again predict functions we'll use for that, and then we'll validate the model by plotting predicted against the actual one. We can use mod also here, that will automatically use the final model, and test data we are going to use here, test data, and run that. Predicted values are there. Now we'll plot a scatter plot, and if both values are matching each other well, then they will have a perfect diagonal line like this. If not match is there, they will have the scatter, and we'll see that scatter. Test data dollar sales price, and that predicted value. Will run that to see object predval. I forgot that predval is there. We'll run that, and you can see that few values are not predicted well, but much of the prediction is there. We can see the correlation also. If correlation is perfectly 1, then we'll see that, we'll say that both the values are matching together perfectly, predicted as well as the actual values, and that correlation is 0.90, means 90% of the values are matching with each other, correlated with each other. that good agreement is there, almost perfect agreement is there. Very few values are these values reason may be some variables which are very away from each other. This is how we fit the linear model, linear regression model, that regression model using the neural network approach. And that's all for this session. If you have liked this video, please click the like button, share this with your friends, and subscribe to my channel if you have not subscribed yet. Thanks for watching this video.